Welcome to The Explainer. Today, we're diving into something super fascinating, the hidden architecture that keeps incredibly complex systems from just collapsing into total chaos. Because whether you're managing billions of tiny electrons, hundreds of thousands of troops, or even the biological networks that literally keep us breathing, preventing a catastrophic failure requires ultimate control. And as we'll see, understanding these hidden routing systems might just be the secret to managing the chaos in our own lives.
So I have to ask, what on earth connects microchip logic gates, the United States Marine Corps, and human lungs? I mean, on the surface, absolutely nothing, right? But the crazy thing is, each of these relies on an incredibly strict, precise system of routing to prevent total system failure.
Let's get into Section 1, the dual meanings of PMOS. Same acronym, different worlds.
Okay, let's look at the acronym PMOS. On one hand, you have the P-channel metal oxide semiconductor. That's a fundamental building block of the integrated circuits inside your phone right now. But then flip over to the military, and PMOS stands for Primary Military Occupational Specialty, the strict classification code the military uses to organize its massive workforce. Now, both definitions of PMOS do the exact same conceptual job. They both rely on incredibly strict classification rules to manage chaotic networks. One routes electrical power, and the other routes human capital.
Moving to Section 2, microscale, PMOS transistors, the gatekeepers of silicon.
All right, to really get how a PMOS transistor works, we kind of have to talk about holes. And I know that sounds weird for physics, but in semiconductors, a hole is literally just the absence of an electron, which actually makes it act as a positive charge carrier. Think of it like an empty seat in a super crowded movie theater that lets people shuffle down the row. When you apply a low voltage, what we call a logic 0, to the gate of a PMOS transistor, it attracts these positive holes. That creates a conductive channel that routes the current. So basically, it's a switch that turns on when the signal drops.
Now, this creates a really interesting engineering trade-off, because these positive holes actually move about 2.5 times slower than the electrons used in NMOS transistors. A PMOS transistor has to be built physically wider just to match the current flow. But here is the absolute genius part. When engineers combine PMOS and NMOS together into a single CMOS circuit, they basically cover each other's weaknesses. Together, they completely eliminate static power drain.
Section 3, macro scale, military specialties, routing human capital.
So just like that tiny microchip needs super precise pathways, the military needs exact codes to deploy the right human asset. The U.S. Marine Corps classifies its personnel into occupational fields. They are essentially turning humans into operational logic gates, which is honestly the ultimate military move. Need kinetic force? Route an O3 infantry marine. Need cyber capabilities? Route a 17 information maneuver marine. This strict classification ensures predictable, reliable capabilities across highly complex combat networks.
You might be wondering, how does a person actually become a PMOS? Well, it starts with the ASVAB screening to establish a baseline aptitude. Think of this score just like the threshold voltage in a transistor we talked about earlier. A recruit needs a specific composite score to basically open the channel to their primary MOS. Once they hit that threshold, they move through basic training and are finally assigned their operational specialty. They are fully routed into the total force structure. Section 4, the architecture of classification, from silicon to biology.
Here's the big takeaway from all this. Both of these systems apply strict classification rules, standardized interfaces, and optimization criteria to manage their complex networks. Whether it's a microchip preventing a short circuit or the military preventing a huge logistical failure, avoiding chaos literally demands precise routing. And nowhere, I mean nowhere, is this more critical than in human health.
Section 5, Biological Routing, COPD Guidelines, the 2026 Treatment Protocols.
Now, what's really fascinating here is that the gold stages for COPD severity, they actually function exactly like a microchip's logic table. Doctors use this highly precise classification to deploy the exact right inhalers based on a patient's lung function. If a patient is at gold stage 1, the output is just a basic short-acting bronchodilator. But if their function drops to gold stage 4, the routing escalates dramatically to a triple therapy. It is literally the body's own PMOS system, strict, optimized classification applied directly to human lung decay.
And just like an electrical grid has to handle massive power spikes, the human body has to handle exacerbations. An exacerbation is a sudden, severe worsening of symptoms. Think of it like a massive voltage spike or an enemy suddenly breaching a perimeter. It completely exceeds normal daily variation and demands an immediate, escalated routing of resources. We're talking things like systemic steroids or antibiotics, just to prevent irreversible lung damage and keep the whole system online.
To combat these exacerbations, modern medicine uses something called biomarker routing. Just like an engineer sorts a slower PMOS transistor from a faster NMOS one, pulmonologists have to sort patient phenotypes. For example, if a blood test shows elevated eosinophils, specifically over 300 cells per microliter, that's a loud signal of immune-driven inflammation. That biomarker basically acts as a switch. It routes the patient away from standard inhalers and toward highly specific biologic therapies like dupilumab, which target the exact inflammatory pathway causing the issue in the first place.
And this level of precision becomes absolutely crucial with breakthrough therapies for severe COPD. Take Ohtuvayre, for example. It's a dual inhibitor that cuts flare-ups by about 40%, which is huge, but it comes with a really steep monthly price tag. Contrast that with roflumilast. It's fantastic for reducing mucus, but it can cause some pretty significant gastrointestinal issues. Selecting between them isn't guesswork. Breathing shouldn't require an engineering degree, right? But ensuring survival absolutely requires precise classification of the patient's specific disease phenotype. You have to route the right drug to the right biologic profile.
But you can't just rely on the active chemical components. You need a solid foundation underneath it all. Non-pharmacologic care is indispensable here. Programs like Carta Health's virtual pulmonary rehab provide remote clinical monitoring and supervised exercise. Just as a microchip physically needs a grounded body to function, or a military needs foundational logistics, a COPD patient needs behavioral systems and rehab to maintain long-term operational success.
Section 6. Universal Systems and Control. The Power of Routing. So, we've seen how the logic of PMOS transistors balances power on a microchip. We've seen how the PMOS military codes precisely deploy Marines across the globe. And we've seen how COPD guidelines use their own PMOS-like logic to route life-saving therapies to failing lungs. They all teach us the exact same lesson. Complex networks only survive through strict classification and precise routing. So, I'll leave you with this final thought to ponder today. Whether managing electrons, soldiers, or breath itself, what hidden system is routing your world? Thank you so much for joining me on this explainer, and keep questioning the architecture around you.